Welcome to the third video in the module on our tandem queuing system. In the first two videos, what we did was we developed the initial model. You can see we have two servers in tandem, and then we developed an experiment and ran the experiment and discussed the experimental results in terms of the s'more plot and the pivot grid and so on. In this video, what we are going to do is we're going to add buffer capacities and the corresponding experimental controls so that we can evaluate our system under different buffer configurations. So as we run our base model, you can see, let me speed it up just a little bit. Let's go from 5 to 10. As our model runs, when server 1 or server 2 are busy, entities can reside in the input buffer for the corresponding server. And so these buffers, the input and the output buffers actually, buffer against the variability in our server and arrival processes. So what we want to do now is we want to eliminate those buffers, and we want to set the capacity of those buffers to 0. And so we need to do two things in order to make that happen. First, I'm going to take our path. So here's our path 1 object, and I'm going to right click on that, and I'm going to convert to type connector. And I'm going to do that for path 2. Let's convert to type connector. And I'll finally do that for path 3. Convert to type connector. And so when we run with path objects, the path has a distance. If I can get the model here, yeah, the path has a distance and the entities have a speed, and so the time that it takes to traverse the path is computed by the distance divided by the speed. When we use connector objects, the entities are transferred in 0 simulation time. So in this case, from the output of source 1 to the input of server 1, this physical distance doesn't mean anything. If I use connectors, they just instantaneously transfer. And the reason we want to do that for this model is because the paths, when a path has distance, it provides implicit buffer capacity. So we have converted those to connectors. Now what I'm going to do is I'm going to go to my server 1 and server 2 objects. So I'm going to select those using multi-select. Over in the properties, I'm going to set the buffer capacities to 0. So set the input buffer capacity and the output buffer capacity. And so what that means is that if the if the server is busy and an entity arrives, it's not going to be allowed to move to the buffer, and so it will stay where it is, in this case in the source. If server 2 is busy and server 1 is finished, then the server 1 will be blocked. So now when we run our model, we're going to see that there are no entities ever in the buffers. We're also going to see that the server 1 occasionally changes to yellow. The yellow basically means the server is blocked. And so server 1 is finished, server 2 is still working, and so since there's no buffer capacity, server 1 is blocked with the entity waiting to be transferred to server 2. So in addition to the blocking, we also see in this model that server 2 can also be starved. So if server 2 is finished working and server 1 is not, then server 2 doesn't have anything to work on because there's no buffer. So even though these speeds are nominally the same, because of the variability, by introducing the capacitated buffers, we have the blocking and starving effect. And so the net effect of this blocking and starving is we're going to reduce the system throughput. So from the previous video we discussed why our expectation is that the throughput with infinite capacity buffers is 48. Let me reduce the number of replications so we can run this. Let's go down to 25. And now with the capacitated buffers, we expect that value to go down because we can't recover from the blocking and starving. There's no buffering going on. And so that's in fact what we see as our replications run. So we're up to about 10 now. Our expected value is 48, and we're down somewhere around 38. So we can go look at the response results here. Let's look at the throughput here. And we can watch as this experiment runs, and we can see the nominal value of 48, we're quite a bit lower than that. And so that reduction in throughput that we see of approximately 10 units per hour is caused by the blocking and starving effect. Now, of course, we can increase that throughput by adding buffers back. So if I go to server 1 and server 2, for example, and instead of saying have 0 capacity buffers, let's just put a 1 there. So instead of having no capacity, we'll now just set those values to 1. So we're either going to have 0 or 1 entities in the buffer. So we can see 1 there and 1 occasionally here. And so the hope is that that's going to reduce the blocking and starving effect. So if we go back to our experiment, now we can compare the value that we'll get now with this 38.13. And so let's run with our capacity 1 buffer. And you can see that we've recovered from 38 to somewhere around 43. So we've recovered approximately half of that throughput that we lost when we had capacity 0 buffers by adding a buffer of capacity 1. And now at this point, clearly the question is, well, what happens if we add a capacity 2 buffer and a capacity 3 buffer? Or what happens if we add capacity 1 to server 1 and 2 to server 2 and so on? And we could continue this experimental method where we go back and change the values of the properties for our 2 server instances as long as we want. However, Simio provides an easier way to do this type of experimentation, and it's by using something called a referenced property. And so what I'm going to do now is I'm going to go to server 1 and I'm going to right click on input buffer, and then there's an option called set reference property. So I'm going to highlight that, and then I'm going to move down to create new reference property, and I'm just going to call this buff1 for buffer 1 capacity. And so you can see as soon as I do that, we now have this green arrow telling us that we have defined a reference property for buffer 1. I'm going to do the same thing for buffer 2. So I'm going to select the object instance, right click on buffer, select reference property, create new reference property, and we'll call this buff2. And so when I do that, now I have 2 properties defined, buff1 and buff2. And so if I select the model properties, we have this new section up here called controls, and we have the controls that we just defined, buff1 and buff2. So here I can set the values for running in interactive mode, so I can set those to say 2, and now when I run I have capacity 2 buffers in both of our servers. And so by defining the reference properties in interactive mode, it lets me specify those property values associated with the model itself. So I can go to my model definitions, and if I go to properties, we've just created these 2 properties. So we've created properties associated with the model. Now the other thing that this does for us is when I go to my experiment, now that we see we have a completely new section in our experimental table called controls. And the controls area lets me specify values for my controls. So I can go in and change these values to 0 and then run my model, and I'm going to get the same value that I got before when I physically set those property values to 0. So by using the reference properties, it's functionally equivalent to going back and setting those values for an individual run. So here's what I'm going to do. Let's reset this, and let's change this back to 10. And I'm going to rename this value S0. And then right below it, I'm going to add another scenario, and I'm going to just leave the default values of 1. Then I'm going to create an S2 and give it a 2 and a 2. And so I'm going to run these 3 scenarios simultaneously. And you can see by defining these reference properties in the experimental controls, it facilitates the experimentation by simply allowing us to change those values without going back into the model. And so I can then compare these systematically. When I go to my response results, get rid of the histograms here, you can see that I have scenario 0, and what I'm looking at here are my throughputs. So I have scenario 0 with 0 capacity buffers, capacity 1 buffers, and capacity 2 buffers, and I can compare those values side by side. So let's go back and let's just add a few more. Let's just add S3 with a 3 and a 3, S4 with a 4 and a 4, S5, 5 and a 5. We'll go all the way up to 10 here. 6 and a 6, S7, 7 and 7, S8, 8 and 8, S9, 9 and 9, and finally S10 with capacity 10. Let me change this here just so we can be consistent. That's S9. And I'm going to run those values. So now that our experiment's finished, we can see that we have run all of our 11 scenarios, and our throughput has, as we should have expected, systematically increased. And we know that we have a maximum value of 48 nominally. When we had infinite capacity buffers, that's what our throughput's going to be. And so when we look at our response results, we can compare these values side by side and see that we have diminishing returns here as we get to somewhere around buffer 4 or 5, that the marginal increase in our throughput as we add buffers is smaller and smaller. And so at this point, if I'm running this experiment, what I'm going to do is try to isolate for, say, these 3 values. I'd like to expand on those just a little bit. So we have scenario 4, scenario 5, and scenario 6. So we can go back to our design, and just on these 4, 5, and 6, let's just increase these values to 25. And note that the status goes to idle because we've only run 10 of our now 25 replications, and so now I can continue to run my experiment. And as I go back, the values that we're adjusting are this 4, 5, and 6, and you can see that we are the s'more plots are dynamically adjusting to reflect the new runs. And so by using these reference properties for our controls, if we're using our reference properties for our buffer capacities, you can see that what we did is we created these the capacity or the capability to adjust the values associated with the model. And then when we go to the experiment, we've created these experimental controls. And by manipulating the experimental controls in the experiment, we can systematically evaluate different alternatives. And so now we've finished our run with 4, 5, and 6, and we can see that probably these 2 values, this is the line of separation here, and these values are most likely not statistically different. Of course, in order to determine that for sure, we would have to do some statistical analysis, and that is a topic for another video. Similarly, we could also use the OptQuest add-in so that we could do some simulation-based optimization based on our control values. And again, there's an entire video series on using OptQuest, and that is something you should definitely look at.